Welcome everyone, and welcome to the fourth event of the Greener Together, a practical guide to low carbon construction. This course is part of a wider project where University of Hertfordshire partnered with the St Albans City and District Council. It was a 2-year-long project funded by Innovate UK. The project aims to achieve to foster the achievement of net zero by 2030, and in particular will empower people and groups to make a difference through innovative behavior changing campaign. What for us is important with this project is to understand that even small choices and have an impact, sometimes invisible, but could help altogether to reduce and target our net zero goals. Saying that, I will pass to Deepti to introduce today's session.
Thank you, Luigi, and thank you, Thomas, for accepting the invitation to be a part of the course. And to introduce you all to Thomas, he's a sustainability engineer and he has 2 decades of experience. And he's been working a lot with the councils, and he's worked on delivering a net zero study for more than about 18 London boroughs. And he's also worked with the housing policy, which is now in place with Cornwall. And he does have a lot of exemplar building projects that he'll be talking about during this session. And this session will focus specifically on how to deliver a good net zero operational carbon building for a new project. And it's sort of looking at fossil fuel free developments or low space heating demand, and how to reduce your energy use intensity and things like that. So before we start off, we'd like to know who our audience are and how you all have a certain amount of knowledge with it. So if you can pick up your phones really quickly, and if you could answer the poll coming up. So if you could scan the QR code on the left-hand side, and if you could answer this question, it would really help us and Thomas know how to address the audience today. Yeah, that's a really nice mix of people we have on the call today. Good. With that in mind, I will hand over to Thomas.
Thank you, Deepti, and thank you, Luigi. Good evening, everyone. So I'm delighted to have the chance to present to you this evening on the topic. So I'll share the screen now. Can you confirm you can see the screen?
Yeah.
Yeah, great. So I'm Thomas from Etude, and I'm going to talk about net zero carbon new buildings in operation. So for those of you who attended the previous sessions, you heard about existing buildings. Here we're going to talk about new buildings, and you heard about embodied carbon, but we're going to talk about operational energy use and carbon. Just a few words so that you understand who I am and who we are. So Etude is a small practice. We work exclusively on making buildings more energy efficient and net zero. A mandate when we work as part of design teams and when we work with contractors is really only this. So this is a picture of my lovely colleagues. We work in 4 areas, so we do quite a lot of work on new buildings, but we also work on retrofit. We develop quite a lot of work for local authorities, as Deepti said, and for the Department of Energy Security and Net Zero. And we also do passive house certification. So I will not talk too much about passive house certification today, but if you've got any questions, I can talk about it later. most of our work is on buildings. So we work on buildings from, very early stages when, it's literally a blank sheet of paper to actually working hand in hand with the contractor to deliver them. And sometimes we even monitor their energy use once they're completed. But we also do guidance and policy project. And, the balance between the two is really useful because the policy project is forcing us to kind of look ahead and understand what new buildings need to do in order to comply with net zero. But then we also bring our experience working on projects, which has taught us, what is easy, what is less easy, what is costly, what is less costly. So I'm hoping that today, you'll have a good synthesis between the two and you can understand what's possible today. But first of all, if we take a step back, fundamentally, when we talk about net zero buildings, we talk about new buildings which should not continuously add to the problem of carbon emissions. So it is complicated for embodied carbon, and you may have heard about it at the previous sessions, but for operational energy use, we're trying to phase out carbon emissions. So you must be aware of the background, of the importance of buildings in the UK carbon balance, of the need to limit global warming, and of this absolutely central step, which has been the Climate Change Act revision towards net zero by 2050. The achieving net zero is not only about, slowly learning to deliver net zero carbon buildings in 2050. It is about complying with carbon budgets. And here we just a visualization of how we could use our carbon budgets in the next 15 years. And as you can see, we need to drastically reduce carbon emissions from one year to the other. And if we keep on creating high carbon buildings, we are not going to do that. So the idea really of net zero carbon buildings is from now on to design and build net zero buildings which stop adding to the problem. So that gives you the framework, but how does that translate into a particular building design and a particular building ambition? So over the last 5 years, there's been really a fundamental rethink of this, and it has been helped by a number of publications. I'm just putting the spotlight on 3 of them here, but there are many others. So the first one is the kind of seminal report by the Committee on Climate Change on UK housing, both new housing and existing housing, which has basically set the direction of travel for the housing sector. The IBA has created a climate challenge, which set very useful key performance indicators in many different areas for new buildings. And finally, LETI published the Climate Emergency Design Guide in 2020, which tried to translate, if you want, the overall ambition into practical recommendations. So let's talk now about what we mean about net zero carbon buildings. Essentially, what we're trying to achieve is buildings which use less energy and not fossil fuels, and buildings which can balance at the building level the renewable energy generation and energy use. For some buildings, it's possible, especially low density housing, where you can have enough solar panels on the roof to match the energy use on an annual basis. For some buildings, high density towers, for example, it's not possible. And for this, you need to invest in off-site renewables. But the idea is to, basically translate the UK level ambition into what we can do on a building by building basis. And if over time we create buildings which, use less energy, for which the level of energy use is matched by renewable energy, I think we are walking towards that ambition of net zero by 2050. So let's start to be more practical about what it means. So there are 4 key principles: energy efficiency, no fossil fuels, renewable energy generation, and low embodied carbon. Because embodied carbon has been covered in another session, I will remove it from this slide and from the discussion today. So we're going to focus mainly on those 3 things. So what we want is to reduce energy efficiency as much as possible, and reducing energy use has many benefits. It will also reduce energy costs. It will also reduce the pressure on the electricity supply network because we're moving towards electrified buildings. The second one is to stop using fossil fuels. So I know it seems strange now, but 5 years ago, it was not a given that, I mean, now it's very clear that you can't call your building a net zero carbon building in operation if you're using any form of fossil fuels for heating, hot water, or cooking. But it was not that clear 5 years ago. Now it's a very clear and accepted principle. That means that buildings need to use electricity for heating, hot water, cooking. And heat pumps are an efficient use of electricity for heating and hot water. So they're, if you want the place to start when you think about no fossil fuel heating, other forms of electricity may be suitable as well. And finally, renewable energy generation, we talk mainly about, building integrated PVs. So let's take it now to a slightly more technical understanding, but it's one thing when you start designing a new building to know which concept you have to embrace, but let's translate it into a number of key performance indicators. The first one is you need to have a building which has a low space heating demand. So space heating demand is the energy you need for space heating. It's affected by the building form, the amount of envelope you have, by how airtight it is, how well insulated it is, the type of windows you're using, the type of ventilation system, and the orientation. So it's a very important metric, and it was referenced explicitly by the Climate Change Committee in their UK Housing Fit for the Future report when they said that the level of space heating we need in new housing should be between 15 and 20 kilowatt hours per square meter per year. And that's actually, to give you some context, passive house uses about 15 or less, and a normal home would use anything between 100 and 250, would have between 100 and 250 kilowatt hours square meter of heating demand. The second important KPI is the total amount of energy used in the building divided by the floor area, and we call it energy use intensity, or EUI. The factors influencing the EUI is, of course, the energy demand in the first place. So the lower the space heating demand, the lower your energy use intensity will be, but it will be also affected by all the systems, by the heating system, by the hot water system, lighting, how much, the cooking and appliances. And the level which is considered a suitable level to call your home a net zero carbon home, for example, is around 35 kilowatt hours per square meter per year. So that's a number we'll come back to, but other numbers exist for buildings other than homes. But for all types of homes, 35 is generally suitable. And then we've got renewable energy generation. So I think there are 2 approaches to see renewable energy generation and how much should be present on a net zero carbon building. The first one ideally is the one of the balance. So let's say your energy use on the left-hand side is 33 kilowatt hours per square meter per year. If you multiply that by the floor area, this gives you the amount of annual renewable energy you should try to generate with your PV system. Another way to look at it for buildings which are more constrained in terms of roof space is just to try to maximize the amount of PV generation on the roof, and you could appraise how efficient you are at generating renewable energy with a given amount of roof space through this metric of kilowatt hours per square meter of building footprint. So as an initial overview, and we'll go deeper in each direction, these are the kind of KPIs for a net zero carbon new housing in operation: space heating demand of less than 15, energy use intensity of less than 35, and a net zero balance. What it means in practice is essentially this, but again, we'll go back to this a bit later. Here we take the example of two semi-detached houses. So as you can see, we've got a well-insulated envelope with, very high-performing U values throughout, a very high level of air tightness, mechanical ventilation with heat recovery, and then a low carbon heating system, in that case a heat pump, and renewable energy on the roof. Those buildings are being built, have been built already. So I'm just going to show you a few examples of the projects we've worked on. This is, an energy positive home, actually, where you can see, some of the features that you saw on that one, especially the very large PV array. This is a building which is being designed at the moment. Another development. So just to show that, you don't have, it doesn't have to be green bling. You can design a building which looks just like a nice modern home, and it can be a net zero carbon new home. But this definition could be applied at a bigger scale. So this, I'm going to show you a development which is currently being built in Haringey in London. So for 270 homes, a variety of blocks that you can see in the middle of the picture. And this is how this development is performing against some of the key performance indicators which I've talked about. So it's doing well on space heating demand, with less than 15, 13 to be exact. The energy use intensity is very low at 27, so compliant with the 35 threshold. On-site renewable energy generation is a bit more of a struggle due to the density, so we can only generate on an annual basis 55% of the total energy use, but it's already fantastic, and the level of upfront embodied carbon is recorded here at 580. This is this building. So again, a message you'll hear, repeatedly from me this evening is we're not talking about buildings for, in 10 years time, 15 years time. We're talking about technologies, a design know-how that exists now. So there is every reason to deliver and design operational net zero carbon buildings now. Another example in Islington, where again we achieved the low levels of space heating demand, of energy use, and there's a lot of PVs on the roof. And more local authorities across the country are setting those rules in their planning policy. So Bath and North East Somerset were one of the first councils to do that, followed very closely by Cornwall Council. And so Cornwall Council, for example, have had a net zero new housing policy in place since June 2023. And it has, it's a success story. It hasn't been easy throughout, but, generally applicants are complying with the policy and embracing the policy, leading to a significant step change in, the quality and the emissions of new housing in Cornwall. So let's talk about the recipe now, how you can design and deliver net zero carbon buildings in operation. So it's a bit of a simplification, but if we want to be really, really simple, we can say the starting point is passive house plus heat pump plus renewables equals net zero carbon buildings in operation. So let's start with passive house. So some of you may know it, some of you may not know it, but it's an energy and comfort standard which has existed for nearly 30 years now. It has requirements in terms of total energy use and space heating demand. And it's a very good quality assurance system. So, it's not only a standard that you achieve during the design, you can actually only, technically speaking, achieve the badge and certification when the building has been built. So there's a very thorough quality assurance process during design and construction, and it's assessed independently of the client and the contractor by a passive house certifier. It's a very good standard because a number of buildings have been delivered, and it's off the shelf. One of the key reasons why passive house has been successful historically is because you may know that the building industry has suffered for a number of years from what we call the performance gap. So buildings are supposed to perform really well, but actually when their energy use is monitored, they use much more energy than they should, up to 4, 5, 6 times more. Passive house has been very good at delivering buildings which perform as predicted. So when you see this bar chart here, you see quite a wide distribution of energy use. This is because every building is different, and you can't control how much energy different people are going to use. But on average, you can see that those buildings have perform in line with the passive house standard at less than 15 kilowatt hours per square meter. Passive house buildings are being delivered, week in, week out, all around the country. These are just some of our projects, but many other people are working on other projects, and it has really started to take off. The 5 pillars of passive house, if you like, how can you achieve the passive house standard? If you really boil it down to 5 key pillars, you would say excellent insulation, excellent level of airtightness, triple glazed windows, no thermal bridges, and mechanical ventilation with heat recovery. So we're going to talk about them, but I'm just going to talk a little bit about a wider definition. So when you design a passive house building, you want to design a very simple building form because it reduces the amount of heat loss area, and it also reduces the complexity of that envelope, so you have less junctions, less thermal bridges. You really want to benefit from solar gains in the winter. So, the south elevation is really important. You want to control shading, of course, but you really want to make the most of this free energy in the winter. You use triple glazed windows because, they considerably reduce heat loss, and you also insulate the envelope really well. But you take the envelope design further by trying to designing out thermal bridges, weak points in the insulation layer as much as possible. You generally add a membrane or a board to make the building really airtight, so you don't want energy to escape uncontrollably from the home of the building. And because you design this very airtight envelope, you really want to make sure that occupants have enough fresh air. So for this, you bring in a mechanical ventilation system, but one with a heat recovery. So it will basically take the energy from the air leaving the building and then using it to preheat the incoming air. On passive house, you need to predict energy use to make the right choices during design and construction, and you do it with a software called PHPP. And finally, sometimes people think that passive house buildings mean you can't open the windows. It's not true. There's no constraints whatsoever. In fact, there's a requirement for every room to have an openable window. So let's explore some of these things which I've touched on. So simple form. So this is an example of a building you see later where we started to get involved with the project. The architect had developed a more complex building form, and we sought to rationalize it. So The trick here is, of course, that the architects have to find a way to make the envelope simpler without making the buildings boring. But architects are generally very gifted and they know how to do that. I wanted to show you this example. So Ashley Road is one of the projects I showed you before, the one which is being built at the moment. And this gives you a feel for, when a form factor is good or not. So generally density, big blocks have very good form factor. Buildings which are quite small have bad form factor. You can generally achieve passive house in every case, but what happens with poor form factors is you have to compensate. You have to add more insulation or benefit more from the sun. So green buildings, in this case, we know it was really easy for them to achieve passive house, whereas the red buildings, we had to work much harder. But in the end, they're all on track to achieve passive house. And yeah, just to be clear, the form factor is the ratio between the total exposed external surface area to the gross internal floor area. The second concept is really to kind of try to make use of the free energy in the winter. So on individual houses, it's pretty straightforward. For when you work on blocks of flats, it could, in urban areas, it could be a bit more tricky because there will be an element of overshadowing from one block to the other. So sometimes you're limited to what you can do, but you really have to be aware of that the more spacing there is between two blocks, the more the building on the left in this case will be able to benefit from winter solar gains, which will help residents cutting their energy use and their energy bills. We're using the example of Ashley Wood here again. You can see that the south-facing facade was brilliant because we could really open up this elevation to maximize solar gains in the winter. Where some other facade was struggling and getting much less solar gains. So again, there are things you can do, but you need to be aware that you need to work a bit harder to make those buildings more energy efficient because they will benefit less from the free energy in the winter. Of course, you don't want to overdo it in terms of, making use of this energy in the winter. So that's why the kind of proportions of glazing we recommend on the south facade is, somewhere between 20 and 30%. Generally, we try to be even, we have less windows on the other facades because you'll get less solar gains and more losses. And the extreme version of that is, of course, the north elevations where, you don't get any direct solar gains in the winter, and you'll have quite a lot of heat losses. So when it is possible, we try to have different window proportions depending on the orientation. And this is an example of another project we worked on. When we started working on it, we actually estimated the proportion of glazing and we realized that they were quite high. And so the revised design from the architect led to more reasonable proportions of glazing, which was really good because, although these proportions may not seem high, with the changing climate and with the overheating rules on new buildings being tightened, this is more or less a building which is guaranteed of suffering from overheating. So beyond achieving passive house, the other reason to go for a reasonable proportion of glazing is to mitigate the risk of overheating now and in the future. There are things you can do, to reduce the risk of overheating beyond the proportion of glazing. This is Ashley Road again, and brise soleils were added to reduce the gains in the summer. So the good thing about brise soleils is you're not cutting the low solar angles in the winter when you want the sun, but you're cutting the higher solar angles in the summer when you don't want them. There are many other external shading devices which are useful at controlling overheating. External roller shutters, for example, are a great solution. And it's more and more necessary to think about energy efficiency as well as overheating when you design the facade. But you really want this envelope to be airtight. This is just a picture of my colleague Katie doing an air test on one of the passive house buildings we are working on. So you're looking at really very low levels of airtightness, and there are different ways to achieve that. We can go back to this in the Q&A if you want, but you're really looking at reducing all these leaks, which are generally everywhere, sadly, in poor construction quality buildings. The mechanical ventilation heat recovery that I've talked about before looks like this. So you're extracting air and you're using that energy to preheat the incoming air. Another picture for one of our projects. So it looks like this. It's pretty big. I've got one like this at home. I'm very, very happy with it because I cannot emphasize enough how not only is it good for energy efficiency, but it's fantastic for air quality. You know, it's filtering the external air. You never have condensation issues with one of these machines if they're well commissioned. So they're fantastic, but they need to be close to the external wall, because otherwise the cold air they carry in their ducts can be a big source of heat loss. So that's why they are very close to the external wall here. So to give you an example, this is another project we've worked on where the ventilation unit was initially very far away from the facade, 10 meters, 12 meters away. And sometimes the ducts would not be a straight line. And you can see both the intake and the exhaust duct drawn on this. So we've worked with the architect to reduce that duct length. So on the right-hand side, you can see the MVHR being closer to the external wall, which is more or less halving the duct length. And it has had a considerable, effect on hot heat losses, reducing the heat losses associated with ventilation by 38%, just by moving the MVHR. We talked a little about thermal bridges and junctions. So junctions are you can reduce them by having a more simple form, but there will always be what we call thermal bridges, because they are just locations in the envelope, if you like, where the heat transfer is not the same as for the rest of the envelope. So what you need to do here is just to have a strategy for each thermal bridges in order to avoid weak points, but also it has another benefit, is you also reduce the risk of condensation in these weak points, because generally that's where the envelope is weak is where you have a chance of having a lower temperature, and if the temperature is too low, then you'll have condensation in those areas. But one very big thing about passive house is that it's not only about the design, it's about construction quality. So you'll see some very, examples of good construction quality here, where the installation has been installed very well, which means that the building will perform as intended. Joints, tapes, no gaps. I'm telling you, not all construction sites look like this, but it makes a very, very big difference. And I'm going to finish the passive house section by showing you a few examples of completed projects to show you the breadth of passive house buildings. This is a very famous one, Goldsmith Street, that most of you may have heard about. It won the Sterling Prize for architecture, and rightly so, because it's a fantastic set of buildings in Norwich, which don't look at all like boring housing. It's very interesting, it's very nice, very comfortable, and the level of energy bills is very, very low. But passive house is being delivered at different scales. This is Acre Grove in Camden, where phase 2 is now underway. Phase 1 has already been delivered. It's high density passive house. And this is the largest passive house scheme in the country, about 1,700 student bedrooms for the University of West of England. So it has been built and certified. And, the type of project is changing. So it used to be, university clients and social housing providers used to be, were the pioneers in terms of passive house because they cared a lot about energy costs for themselves or their residents. But we see private clients nowadays being interested in passive house, and this is a fantastic project in Earl's Court, which is targeting passive house. But it's not only for residential buildings. This is a school which we've certified or in the process of certifying in London, which has been built. This is a university buildings for the University of Oxford, which is progressing on site. This is an image of the energy model. It's on track to achieve passive house. So we talked about passive house. We're going to move on to the second key ingredient, which is heat pump. So it is obvious, but it's never a waste of time to talk about it. Fossil fuels are not compatible with net zero. And the key reason for this is the scale of emissions associated with fossil fuels is absolutely colossal compared to a heat pump. It's 10, 20 times more. So even compared to direct electric, the emissions of carbon associated with gas boilers, either individual, communal, or from district heating, is really, really bad. So we started a movement called End Gas Now a few years ago, the idea being to stop putting gas boilers in new or existing buildings. The level of heat pump rollout is increasing. So a few years ago, it was about 20,000 units a year compared to, say, 200,000 in France or Italy. We're up at 65,000 a year at the moment, but as you can see, the level of installations that we need to really achieve our climate targets is much higher. So yeah, there are encouraging signs, but much more to do. You may know what a heat pump is about, but just to be clear, so it is using a source of heat, which can be the air, could be the ground, could be groundwater, and adding, if you add a little bit of electricity, by using a little bit of electricity, it transforms that heat into high-grade heat with a good level of efficiency. There are different types of heat pumps. I think the most common one is the monoblock system, where you have an external unit and a hot water tank in the house. So it looks like this. There are also heat pump systems which are a bit more unusual. So you've got the exhaust air source heat pump, which uses the air coming from the home, as opposed to, and it doesn't need an external unit. We can talk about this one later if you want. There are also some communal forms of heating. So the most common is actually this one. Oh, sorry, there's a problem with the label here. It's not a ground loop here. It's an air source heat pump. So you've got air source heat pump on the roof of the block of flat and some big hot water tanks. And then heat is being sent to heat and face units in each flat. But you also have better and more unusual setups. So this is a ground loop, which is basically circulating water at around 13, 15 degrees to what we call shoebox heat pumps in each unit. Just some pictures of what basic heat pump installations could look like on homes. So they could be located, often they're in the garden, front garden, back garden. This one is my own heat pump on the roof. And so Plashet Road is a building which has been completed a few months ago, which has a communal heat pump system. It's fossil fuel free building. Melfield Gardens has been handed over today, I think. It's a passive house scheme in South London for Phoenix Community Housing, and it's a fantastic scheme. And they use direct electric panel heaters and immersion heaters. So again, fossil fuel free. And now we'll move on to the last piece of the jigsaw, renewable energy. So really, we need to embrace a culture where PVs play a big part in our building design. so far, there was a bit of tokenism going on where, a few panels were enough, but the potential for our roofs to generate a lot of energy is very significant. Not only is it good for carbon emissions, but it's good for energy bills. I'll illustrate that later. And I just wanted to put some numbers here to show you how variable the amount of energy you can generate per square meter of footprint changes depending on the roof design. This is just a few examples of projects. The top is a school project we worked on where, we've really tried to maximize the area of PVs. In the end, there's less panels than what we're hoping for, but still quite a lot and much more than on a normal project. And on a house, it would depend a little bit on the orientation. One thing to note is that putting panels on facing east and west is perfectly fine. So don't think it should be south facing only. I'm going to show you a few examples of nice installations. So this is a very nice flat roof installation with what we call a concertina arrangement, which is really, really good for flat roofs. This one is interesting. It's not a concertina arrangement, but they didn't let the plant room go in the way of maximizing PVs. This one is in America, and you've seen this one before, Caston House, a fantastic monopitch roof covered with PVs, a scheme in Germany, which maybe is a bit more polarizing, but incredibly wonderful at generating solar energy. And this is another apartment building in Germany. Very interestingly, here again, it's a monopitch roof for a block of flat, which but with a fantastic PV installation. So we've talked about technical solutions. We'll talk a little bit about costs. So when you deliver a net zero carbon buildings, there are generally additional costs and cost savings. If we look specifically at the energy efficiency side of things and putting aside heat pumps, because heat pumps are likely to be mandated, but so in red you've got the clear additional cost. So you need better windows, a mechanical ventilation system with heat recovery, thicker external walls, really well insulated, and better contractor supervision on site. So they're clearly additional cost. The elements in orange are also additional cost, but they tend to be more marginal in the great scheme of things. It depends, of course, on the project. And then finally, I want to highlight that there are cost savings, that net zero carbon buildings tend to be less complex buildings, so they're cheaper to build. Because you've improved the form factor, there's less envelope. So, it's more efficient as well, most cost effective. We see the difference on projects when we get involved that our involvement tends to reduce window proportion slightly. So there's a bit of cost savings there. Because they're more efficient than this, they need less electricity. So the savings on the electrical infrastructure and on the heating system. And for projects which have to pay for a carbon offset fund, of course, you don't need to because you're net zero carbon building in operation. We've worked on many projects with Curry and Brown, who are cost consultants, to kind of quantify what kind of additional costs we're talking about for net zero carbon new buildings. And here you can see a range of additional costs for the Isle of Wight. With the Isle of Wight wants to know how much it would cost to build to net zero. And as you can see, it depends. It's generally cheaper for block of flat than houses and cheaper for houses than bungalows because bungalows are less efficient. But we're talking about, between 2 and 8%. But very importantly, they have a fantastic potential to reduce energy bill. So this is a comparison of how much a resident pay in a net zero carbon buildings compared to in a home compliant with the non-plan, which is already a fairly good standard. And as you can see, the potential for benefit, it's halving energy cost. And a very important part in this, is of course about energy efficiency, but PVs really have a key role to play to represent a saving, because it would be free electricity if you're able to use the electricity used by PV straight away, or you can sometimes get a little bit of money from exporting. But really, the key incentive is to use the energy you're generating, and if you're able to store that energy either in a hot water tank or in a battery, that would help considerably reduce your energy cost. So I'm going to just talk briefly on quite a technical aspect, but it is quite important, so I wanted to cover it. Is there any questions? We can go back to it later. What you can see on the left-hand side of the screen here is the metric used by building regulations. So to comply with building regulations, you have to achieve an improvement over what we call the notional building, essentially the limit. But this metric has a number of problems. It's not very clear. It's not a physical metric you can measure. It's very difficult to understand. The net zero carbon metric, which I've talked about, they are meant to be measured on site. They're meant to be understood by all professionals. So if we embrace them, they will create a vicious circle where we understand better and better how good we can be and learn. Generally, at this moment in time, partial modeling, so the modeling you need to do to demonstrate compliance with building regulations, is not suitable for net zero carbon buildings in operation, in the sense that they are not good at predicting energy use. It is changing. The home energy model for domestic buildings is supposed to be delivered later this year and will be much better at predicting energy use. But at this moment in time, if you're working on a net zero carbon building in operation, we strongly recommend that you use predictive energy use modeling, and in particular PHPP. Why? So this bar chart shows you the difference of energy use assessed by SAP currently compared to PHPP. As you can see, the assessment on the left side is wrong for many reasons. And so if you develop your design informed by this tool, it's not going to give you the right information. So this is a table, comparing SAP, which has to be used for every domestic building, to predictive energy modeling. But encouragingly, beyond those differences, home energy model HEM is coming, and we're hoping that it will be good enough to be used for predictive energy use modeling. And I'll finish with now just a few slides on the UK net zero carbon building standard. So it is a rule book which is applicable for different sectors. It tackles carbon, energy, and it's science-led. It has been developed by a range of institutions who have come together to develop it. It sets targets in a number of areas. So as you can see, you need to report and meet limits in a number of areas. Upfront carbon, operational energy needs to be fossil fuel free. If you're connecting to a district heating and cooling networks, there are requirements. There are also requirements in terms of refrigerants. You need to meet some on-site renewable energy targets. We've discussed them. And then you need to report on other things, but there's no limits. So life cycle embodied carbon, water use, electricity demand, and heating and cooling. So it's a fairly technical document, but I would really recommend that you look into it. What is illustrated here is two metrics that the standard is dealing with. So in orange, you've got the energy use intensity. So as you can see, this is the level of energy intensity you have to comply with to be compliant with the standard. And as you can see, it's moving slowly from, I think, 38 towards 35 kilowatt hours per square meter. and the embodied carbon targets are reducing more drastically over the few years, tending towards zero by 2050, hopefully. So it's time to summarize. So to leave you with a kind of concise definition of a net zero carbon building, I would say it is constructed with a low level of embodied carbon. It is energy efficient, fossil fuel free, and its net annual operational CO2 emissions are zero on an annual basis as renewable energy generated on site or off site when it's not feasible balances on an annual basis the energy it is using. You can see at the bottom a few elements that we've talked about today. So I think that I'm hoping that my presentation gave you a decent overview. There are things we discussed a bit less perhaps that we should have, like energy flexibility, but very happy to talk about it later. And there are nowadays more and more guidance on net zero carbon buildings. This is a piece of guidance we done for 4 councils 3 years ago. And we did our best for the guidance to be accessible and clear. So if you want to find out more, I would urge you to investigate. I would be happy to share with you some of these links. That's it for me. I hope it was interesting, and I'll pass on to Luigi.
So much. It was interesting indeed. We have the first question, which I put on hold because I arrived really at the last few slides. So I think it was better discussing this at the end. And it's by Milin. Milin, would you like to ask the question yourself? Okay, we're gonna read then. So you can read yourself. Thomas is in the chat. Could you read the chat? Should I read the question?
No, I mean, the short answer is no.
Well, I think it's good to say we'll read this question first because maybe the recording we don't have the chat. Is it possible to use Partel equivalent for national buildings comparison from project outside the UK?
Thank you, Luigi. Sorry. Yeah, so the short answer is no for a few reasons. Partel has been really developed for the UK. That's the first reason. The second reason is that, Partel modeling generally, is based on UK weather data. So if your question was about Partel modeling, the answer is no. If your question is about the specification, so for example, the consultation on the Future Home Standard has a number of specifications for the notional buildings. If your question is, would those specifications be okay in other countries, then it really depends on the weather. For weather which are comparable to the UK, yes. But when the weather is different, be careful because, the balance of energy use changes and it may be less important to do a certain thing, more important to do others.
Thank you for the question, Melina. Thank you for the answer, Thomas. We have an active question by Alex. Alex, would you like to ask the question yourself?
Yes, sure. So can you implement the NVHR into like pre-existing flats that like have boilers? And if so, how can you like justify it to the landlords who aren't really as concerned about the environment?
Yeah, thanks, Alex. So yes, absolutely. So MVHR is being retrofitted in homes. I retrofitted MVHR in my home. There's no contradiction whatsoever with the heating system. It has nothing to do with the heating system. It would purely deal with ventilation. The problem you have with landlords in general is, especially if they're not interested in the environment, is, they take up space. They are quite costly. And so generally, they are very appealing to people who are really interested in creating an energy efficient and very healthy environment. So, for example, people who suffer from respiratory, problems, or people who live in cities on a busy road will find MBHR very appealing, but landlords who will not live, in the flat may, you may struggle to convince them. So, try by all means, but it's not an easy sell because they cost much more than the minimum they have to do.
Thank you, Alex, for the question. Thank you, Thomas, for your answer. Any other question? Feel free to type or to ask the question. We have CD. CD, would you like to ask a question yourself?
Hi, yeah, sure. I would like to say, first of all, very interesting presentation. Thank you, Thomas. It was very detailed. And basically, I wanted to know more about heat recovery and how I can try and implement that in my design at the very basic level while designing my project.
Yeah, thanks, CD. So there are two types of heat recovery systems nowadays in especially in new housing design. The main one is mechanical ventilation with heat recovery. So we talked about this one first, and then there's wastewater heat recovery. So mechanical ventilation heat recovery, as I said, everything is happening in the box. What's happening when you don't have mechanical ventilation heat recovery is generally you have trickle vents in the windows, those little holes essentially, and a fan in the bathroom which is sucking air. So the bad thing about those systems is that you drag air from outside directly in each habitable room, and then you expelling it from the kitchen and the bathroom. When you bring air, and it's winter, the air gets into the home at 0 degrees. And of course, you need to heat up the air. So, your boiler or your heat pump needs to work to heat up that air. When you use a mechanical ventilation with heat recovery, instead of taking air through the facade, you would take it through a single duct connected to the MVHR, and then you will go through a heat exchanger within that box, which is a plastic heat exchanger, and it would preheat the income. You would get energy from the air which is extracted, but there's no contact between the air. That it's different. They cross each other, but without touching each other, if you like. And so you get the energy without getting the CO2 and the pollution. So that's mechanical ventilation with heat recovery. There's another system called wastewater heat recovery, which is a system you basically you apply the same principle with water. So you would get the water from, say, the shower tray, and you would collect it, and you would use it to preheat the incoming water. So you have to heat it less than if it was water coming from the mains. This is getting common, but it's not, it's more easy to implement in houses than flats.
Thank you.
Yes. Thank you so much.
Thank you. Any other question by the audience?
So could you elaborate on what you meant by energy flexibility?
Yeah, thanks, Alex. Very good question. So we're moving to a world where virtually all buildings will be supplied by electricity, and it will be their only source of energy, right? Electricity supplies to each building. Which means we're moving to a world where the electrical system in our buildings will be interconnected much more. And the idea of demand flexibility is for buildings to play a part in the electrical system. And by playing a part, I mean they need to be able to use less energy when the electrical system needs to produce a lot of energy, and use energy at a different time. If we don't do that, it means we need to continue to build power stations which are able to deal with the peak, but will most of the time not be required. And that's going to be very costly, and ultimately the consumers are going to pay for it. If you have a home which is able to, for example, stop the heating system for an hour without having to see its temperature go down because it's very efficient. Or if you're able to store energy at night in your hot water tank to use it in the morning instead of having to heat your hot water in the morning, you're helping the electrical system. So what we call energy flexibility is about defining the ability of a home or a building to use electricity in a flexible way to work well with the electrical system. Is it enough, Alex? Or?
Yes, it is. Thank you.
Thank you, Alex. Again, Thomas. CD, you have another question?
Yes, yeah. Just to think upon the question that I asked earlier, would it be better than to place the kitchen where we produce or we heat stuff near the natural air flow where we get air from, and which would naturally then let the hot air be transferred to the colder rooms, like some kind of vent at the topper end of the wall or something. Just
Yeah. So thanks. I think your idea makes sense in terms of thermal energy, but unfortunately not in terms of humidity. So, the kitchen and the bathrooms are places where humidity will be created. And generally, you want this
Right.
humidity to leave the building. Otherwise, you create condensation issues, which could be bad in many ways. So what tends to happen in ventilation system is, you provide fresh air to the living room and the bedroom, and this air is actually slowly being sucked by the kitchen extract and the kitchen valve and the bathrooms, and then it's making its way out of the building through the heat exchange.
okay, yes. All right. Thank you.
Thank you.
Thank you. Nick, you have a question? Would you like to ask the question yourself?
Yeah, sure. Yeah. Hi, Thomas. I think you hinted at it, but are you experiencing many problems with defects, particularly around air tightness and things? Because you're obviously expecting a higher standard than is traditionally achieved with our trades.
Yeah, thanks, Nick. I mean, yes, but I will be positive. I think that, we work on very efficient buildings. We work with contractors who have never done it sometimes. And, it's a very positive experience because it's about construction quality. So, and in our experience, most people on site, they want to do a good job. And so, as long as they're clear on what we're trying to achieve and how to achieve it, I'm not saying it's always perfect. Sometimes things need to be redone or modified or checked, but it is largely a very positive story. I think there are bigger issues when people don't care. So when people don't check, when people don't explain, and they're setting, high expectations, thinking that everything can happen magically on site. But I think when you have a practical, straightforward conversation with people delivering the air tightness strategy, for example, it's a success at the end. The level of air tightness we're achieving on blocks of flats, for example, on Ashley Road last week, we achieved an excellent level of air tightness, which people were saying 3 years ago is not possible, that for buildings of that scale. So I think it's typical of these things which you think are challenging, you think are impossible until you do them and you realize that actually it's fine.
Thank you. Alex, another question, please.
So earlier when you were mentioning about the need for reducing the carbon emissions in your energy budget, how can we actually follow that budget if sometimes like the ones that use the most amount of energy tend to be the ones who don't want to implement these measures whatsoever?
It's a
Like,
very deep question, Alex. If I knew the answer, I would write a book. Honestly, I mean, I've been working in this field for more than 20 years, and the only thing I would say is that along with the technical work that that we do, that others in this room are doing, we always have to ask ourselves, how can we make it clearer? How can we make it more appealing? How can we make it more mainstream so that it becomes the norm? And I don't think we are there yet, but we are so much further than we were even 7 years ago. I think I've noticed in this country, when Extinction Rebellion did something in 2019, I think it was, which happened to be at the same time of the net zero commitment, I think things changed. We got to another level of understanding, commitment, and so we see projects now which we would only have dreamed of 10 years ago. I'm fully aware that we're probably going now to the next phase in the net zero challenge, where people are going to be more openly contesting it. I think it's sad to see, but we're starting to see people using it for political advantages. A certain challenge against net zero. I think it was always going to happen. It's happening now. We'll have to deal with it, but there's so many reasons to do it, energy bills for residents, construction quality. And the more that we prove that it's possible and that the premium to achieve it is quite small compared to the benefits, I think we're on to a winning strategy. But we still have a mountain to climb, obviously.
Thank you. Thank you, Alec. Thank you, Thomas. Any other question from the audience? Again, feel free to type in the chat. Yes, Alex. Please ask the question.
Hello, hi Thomas.
Hello.
This kind of relates to Nick's question. What are the most common challenges that developers face when trying to meet Operation Net Zero standards, specifically in new buildings in the UK?
So I think at the moment, viability is really challenging. So in this kind of adverse environment, it's very tempting for developers to reduce the ambition from the outset because they know that viability is such a big concern. And I've got some sympathy for this. You only have however, we've been really amazed by some clients who have adopted a much more pragmatic approach. So two of them are having a council or Peabody, the social housing provider. And Peabody have developed quite a nice system called the twin track system. So their ambition is to deliver passive house, for example, and net zero. And they want to stick to that level of ambition, but along the way, they will identify cost savings. And if at some point they need to save money, then they will action those cost savings. So, but they really try to maintain the ambition. And I think it's a very pragmatic way of dealing with the situation, because otherwise, viability as a concern is going to damage the ambition. So I think viability is number one challenge, and how you navigate it. I think that skills are a potential challenge, both on the design team and among contractors, but it is changing quite quickly. I think, 5 years ago, the number of contractors who could evidence having delivered passive house was very low. Now it's much more common. People have got much more appetite for this. As a result, they price the risk much more, more differently. Before people used to slap a cost premium on passive house more than now. So yeah, I think viability, skills are the main ones. I can't think of any supply chain constraints or yeah.
Okay, thanks so much for that response.
Thanks, Alex.
Thank you both. Question and answer. Any other question from the audience? Again, feel free to type the question or ask to intervene and ask a question yourself, Thomas. Being very practical with the question, which I think is the goal of this event. So really how we can apply all this knowledge. It's not just knowledge that is in the hair, is that knowledge that's in the book, or is knowledge that, let's say, professionals have. It's a knowledge that everyone needs to know. And of course, we are in the chat, maybe future architect, people working in the built environment. And I think this practical approach is what we need, because as you said, everything that we can achieve today maybe was really impossible to achieve just 3 years ago. And this trust and this push towards net zero, towards a sustainable world, I think give a big push to the advancement in the discipline and the built environment in general. Do we have any other question? If we don't have any other question, I will invite Deepthi to join us on the floor.
Yeah, sorry.
Virtual floor, of course.
I will share my screen again. Can you see my screen?
Hold on, it's coming. Yes.
Yeah. So if you can answer the next question, or let us know what your key takeaways from this session was and what you learned from this session, that would be great for us to get a feedback. That's a good takeaway. That's really nice to know. Do you have any comments, Thomas?
No, I mean, I think that I really like the comment about rapid positive progress being achieved, because it's what we see on the ground, and it's very encouraging. It's so possible to design and build better buildings, which better for the environment, better for the residents, and still look really good.
Yeah, I think there's that notion that sustainable buildings cost more in the initial stages. So is it really worth doing it? That's a big question that a lot of people put in the forum. So I mean, this is great feedback. So thank you, Thomas, for being a part of the course.
I mean, thank you, and thank you everyone for attending and giving your time. It was a pleasure to talk to you this evening.
I believe, going back to what Deepthi was saying, I think what we learn, our audience are learning. I think we're gonna have like typical audience on the section. We have audience coming to all of the session. Is that we need to start like focusing on a specific aspect, and where we're looking at cost, the cost is spread over the life cycle, and an investment is for for the life of the building at least. And sometimes it could be even longer than our life. We never depend by building. If we think about infrastructure projects, sometimes have really long life cycles. I would like to thank you, everyone. I would like to first thank you, Thomas, for the incredible presentation, and what we take from this presentation is a lot, I think. There are good comments on the chat of people saying it's a really good webinar, very positive, great presentation, Thomas. These are all for you. Thank Deepti to coordinate these and helping both the university to achieve this incredible course, build out this interview course. Before wrapping this up, I would like to share my screen, and in particular, this is the next event. We had Laura Baron talking about Operation Net Zero in retrofit building. We had Mirko Parnetani talking about embodied carbon in the building or life cycle. We had Christian Dimbleby, impact of natural materials in building. And today we had Thomas Laffer, operational net zero in your building. We're looking to see all of you again on the 3rd of April, where Duncan Barker-Brown will talk about circular economy and innovation. Thank you again for attending today. Looking forward to see you in the next event. Thank you again, Thomas, and have a good the rest of the night.